So good evening. My name is Aishan Rao. This is the 8th or ninth interaction session for this. Today we are going to mostly look at only at the CNN part, and that too from the perspective of theory as well as the code. In the first half, we will look at the mostly cover the theory and we'll start the coding. And in the second part of the session, it is after 1 hour, we will start off with the CNN part using PyTorch. So let me share the screen. Um, just a minute. Okay, I hope you can see my screen. Yeah. Okay, so let me, yeah, I think that would be fine. Okay, so we will start with basics of CNN. CNN is convolutional neural network. So we will go step by step. I will just give you an overview of with respect to it. Why do we need convolutional, and what is the importance of this? You might have heard this CNN network a lot. Maybe if you are accustomed to the deep learning, if you have little bit background of the deep learning terminologies here. So it's one of the important thing, and mostly it is used for images. Like if you want to process some images, if you want to learn like image classification, or just want to identify, detect the edges of the images, or some any operation with respect to images, at that point of time the convolutional neural network come into picture. Okay, so it's one of the basic standard models, like the fully connected neural network that we have seen from the beginning, and and the sigmoid neuron with the feed forward networking with backpropagation, and all that, but we have seen in the context of the fully connected network. So what is fully connected network? So before going to this, first we'll just have a brief recap of fully connected neural network, which you also call as feed forward network with back propagation. Okay. uh, okay, so a fully connected network is simply a set of layers. Input layer, there's an input, this is an input layer. Okay, just let me create one such that I will maybe better able to understand. Let me change the color. So this part, the I'm highlighting with red, this is called as input layer. This is a hidden layer, and this is output layer. Okay, now fully connected means that my each neuron at the input layer or the previous layer will be connected to each of the neurons in the upper layer. That's the only that's the major this thing, and that's what we have started learning with respect to it, right? So this nothing much fancy. It's in terms of conceptually, it is very simple to understand that a fully connected network is each neuron is connected to each other neuron within the between two layers. Okay, now we have, based on that, we collect we try to we aim to teach, or maybe, or rather we aim to teach the machine, try to learn the weight and bias parameters, right? Now convolution is little different. So convolution is little different with respect to it. We will see how it is different, but let first try to understand why we need to reach to here. Okay, so what is happening that so the one of the positive point of this fully connected network, like this is a very simple network, we can extend number of hidden layers and all that. So this universal approximation theorem, UAT, it tells that based on this theorem, we will say that deep neural network, or this deep fully connected network, are powerful function approximator. That means, so at the end, so what we are trying to achieve using any neural network is basically that we have an input x and we want to create an output. So we need to find the f of x. Basically we need to find this function x such that it, given any input x, I need a particular output and should be close enough, right, or exactly or close enough. So this DNNs are functionally powerful function approximator. That is, it is able to find that given function of x such that it can accurately or approximately able to identify the particular output that we need. So that is proven by UAT. Okay, and it, because of the backpropagation, we can try to learn the weights in a much better way. Okay, so backpropagation give us the more advantage with respect to it. Now, but there's a downfall of the fully connected network also. Now, what is that? That DNN are, these are prone to overfitting. That means, so if I'm learning a particular data, training data, so what it will, the DNN will try to learn the exactly whatever the input of given training data is there, it will try to learn exactly as it is. Okay, so this case will lead overfitting, because if we exactly try to learn or almost close to the learn that how the training data is, when the test data will come where we haven't trained the model, there the model performance will become very bad, right? So this is a not so good quality of any deep learning network. So that's why we need to avoid this overfitting aspect. Okay, and also there's a concept of gradient vanishing. uh, Gradient vanishing come into picture because when you do a back propagation, you try to calculate the gradients of a particular weight with respect to loss, right? So for example, okay, so like I need to now, I went to one pass, I went till up, I learned something, I assigned it some weight here. So you can check on the green, I'm highlighting with green right now. So if I want to update the one particular line from the input to hidden layer, I have highlighted with green. So if I want to update it based on my whatever, based on my what I loss I got here at the output layer, so what I will do, I will again go back propagate and I try to find a gradient of that particular weight. So let's say it is weight 1 to 1, something like that. So what I will do gradient wise, so with respect to loss, I will try to find the gradient of 2 1, and I will try to find the gradient of the particular weight, and I will adjust the weight W21 with respect to learning rate into W21. This is how we update a particular any weight vectors as of now, right? So what happens is, if I have a very huge network, that means instead of having here any one hidden layer, I have a multiple hidden layers, maybe 2 or 3 or let's say 5 hidden layers. So my chain of going from coming from L to W21 will be very high. So for example, let's say I have 5 hidden layers. So my to reach here W21, that is to input layer, I might have to go from so there's something called as pre-activation activation function. So I will have to go here maybe at the 5th location dot, then sorry, h activation function, and then from activation function I have to go to pre-activation function, then uh, h4 with respect to a5 with respect to h4, kind of like that till I reach to a place where I can say that it is a1 a2 with respect to w21. So it's a quite big partial derivation kind of thing, and here what happens is gradient can vanish. One of the gradients here, if I'm highlighting here, I'm highlighting red right now, here any one of them might lead to 0, it's not updating its value too often after multiple epochs. At that point of gradient vanishing problem will come into picture. Okay, now for that we have seen in the course multiple techniques, like we have seen the concept of weight initializations, multiple weight initializations. As of now in the course, we have seen regularization with respect to, you might have heard of L2 regularization as of now. Okay, and some activation functions we have seen, right? So multiple things we have tried to improve these things. Okay, but still the problem is, the main problem comes is that in the fully connected network, that a DNN function or deep neural network or fully connected network is very complex. And why it is very complex? Because it has lot of parameter. Okay, so the more the number of layers, the more number of weights, because each weight for each neuron I have to calculate. right? So I have this here in input layer. Let's say I have 100 inputs, 100 inputs, and here hidden layer I have 3, right? So I have to, for each weight I have to find 3 go from one layer to the input layer to the hidden layer. I have to calculate approx 300 parameters, and this is very simple parameter. As we go more and more complex, we will find that the number of parameters will increase more and more, right? So the problem with fully connected network, it is complex. That's not a problem, but the problem is that we have to do a lot of computation because it has a lot of parameters, right? So, and because of it has a lot of parameters and it can do a lot of calculation, it's prone to overfitting. Okay. Now, if we can understand this part, that fully connected network is because of this, that it is very complex, it has a lot of parameters to calculate and is prone to overfitting. Now we will come back to something to understand that, okay, can we deduce something here? So our task will be, or what we can say here, that can we have a model which has which which remains a complex model, but the number of parameters we need, that is the weight and biases, number of parameters are not that much extreme, are at a decent level. Right now, just say as a decent level, right? So let's say that instead of calculating maybe 1 million parameters, maybe I will try the same model. I can learn the same data, I can learn with maybe some thousands of parameters, right? Instead of putting millions of parameters, maybe some 100,000 parameters can I learn from that. So this is my aim. Yeah. So here this one concept of concept will come in, to help us with respect to this. Some concept will come as convolution. So it's a typical mathematical operation. So convolution operation comes into picture. So what it is saying, convolution operation is that, to give an example from the course itself. So let's say we have a plane, okay, and so at time x0, I have certain speed, okay. At time x1, I have certain speed, and at time x2, I have certain speed. Okay. Now what I want is that I want the exact average speed over the duration of a course. So let's say I'm in Tirupati right now, you might be in Delhi. So I need that at particular time interval, what is my average speed would be like, okay. Because instantly every time the speed might be changing by few numbers values, right? But I don't know, I just want an average value with respect to it. So what I will do, this is a current timestamp at right now, that is okay, that it is x2. So what I will do is I will go back and see the weights or the values at different timestamps, its previous timestamps, like this x1 and x0, okay, and I will assign certain weights to them, okay. So at current timestamp, I will say maybe it as at 190 kilometer per hour kind of thing. In x1 times it might be a 180. At x0, maybe the starting of the plane, it might be at maybe 160. Let's assume like that, and I will assign certain weights with respect to it. So I'm just putting -1 because at current position we have 0, so my -1, the previous timeline will become -1, right? And I'm assigning certain weights. Why do we assign weights? Because I want to assign the priority, that what if I have certain data, how much priority I should give to that data, right? So as the older data gets, its value will becomes very less for me, because I will assign more value to the current timestamp and its previous timestamp, maybe not at the third timestamp. Okay, so what convolution do here is, it's in a similar way. What it will do, that to find a certain value, convolution operation in a typical mathematics, what it will do is it will consider previous values, okay, and it assigns some weights in that, some weights, and use a certain operation, some mathematical operation, let's say summation, like this summation, and use summation, sorry my English, uh, to find the current value, okay. So for example, let's say I have an array. Okay, so here I might have, for the flight I might have 160, 180, 190, 170, 190, maybe 180, kind of like that. So in this I have a different timestamps are there. Okay, and this is the flight speed. Okay, so if I want to calculate maybe the 170th thing, that means at x, let's say x0, x1, x2, x3, x4, x5. So x3 timestamp, at this timestamp I want to calculate what might be my speed would be, and I will assign certain weights to here. So maybe because I know the current timestamp speed to 170, so I might assign certain values, let's say 0.5 value into this. At 190 I might assign 0.3 because it is little older timestamp for me, and I will decrease it because as my data is getting old, I will assign less and less value to it here. So that's how I will maybe try to assign certain values, and I will do a summation of that. That means 160 into 0.1, 180 into 0.01, kind of like that, and I will try to find what is the my flight speed at x3 timestamp. Okay, now if you're able to understand this part, that I need to find certain values, and what I'm looking at past data. Okay, if you are able to understand that part, that is more than sufficient. Now let's build on top of it. So what we are looking at here is to find certain value. I'm looking at neighbors, basically they will call us neighbors here, or the past values of it. Okay, now what happens in a actually convolution, because we are dealing with image, let's say it's a 2D matrix as of now. Okay, image is a 2D matrix. So what convolutional matrix will do, here I will introduce the concept of kernels here, kernel, and this is the input. The kernel you can also consider as a weight as of now. So that is totally basically these are the weights, and I am trying to calculate some output out of it. Okay, so if I want to know output of okay, let me define here. So A, B, C, D, E, F, G, H, kind of like that. So and here W, X, Y, Z, kind of thing. So if I want to calculate the F value here, what I will do is in a typical convolutional in a setting, what I will do is I will try to, I'm making a blue box here, I will try to look at its neighbors, and I will try to multiply it with its kernel value, that is the weights. Okay, so why do I need that? To find the value of f here, to approximate the value of f, because I am trying to learn it, right? So eventually my part is to learn that if it is an image, input is an image, and at f pixel, because each point is a pixel right now, so at each pixel, in this case f pixel, I want to know that what my value would be. Okay, so for that I learn and I initialize certain weights, in this case which we name as kernels. Now what I will do, I will, to calculate this, I will look at my surrounding neighbors, I will multiply them with kernel, and I will get some output value. Okay, that output value, basically a typical I will get a scalar output here, so that is totally fine, and I will use it to scale a value, and whatever the after, like it is will like f into w plus g into x plus j into y plus k into z. Okay, so if I do this thing, I will get certain scalar value, and I will use this value, let's say f dash, I will put it here. So that is how I am trying to reconstruct my image for whatever operation I am trying to do. Okay, so this is a typical this whole process is called as convolution. Okay, so I am depending on my neighbors, on my neighbors data, plus I am depending on the kernel values. Kernels here are weights. Okay, so I'm using interchanging the terminologies, just keep that in the mind. Okay, so I'm using this well to find a value of a particular pixel. Okay, this is simply what convolutional we are trying to do. Okay, now if you able to held it here. Now let's see what else we can do here. Now, since we are able to do convolutional, now this is a typical mathematical operation that we are for calculating one value, we are calculating, we are considering all its neighbor value plus we are calculating with certain weights assigned to it. Okay. Now, as a CNN model, my task will be to as a CNN model, I will give my input as it is. My model task would be to learn this particular kernel, and this kernel will be of any size right now, but we usually deals with the n cross n, right? That is in order of same numbers, that is 2 cross 2, 3 cross 3, kind of like that. So we use the kernels, we try to learn the weights, certain weights, and try to predict that what, so given an input image, whether we can reconstruct the output image as it is or not. Okay. So a lot of other theories then behind, but if we are able to understand this convolution operation that we are using this, that is more than enough. Okay. Now what is actually happening right now in the what we are going to do right now and what is actually happening, let's see that aspect as well in a typical CNN. Okay. So now when we talk of an image, right, image, we might say let's say a Taj Mahal is there, right, a Taj Mahal is there. Okay, so we might say that it's a 30 cross 30 matrix. Okay, that's how we'll see. Okay, it's a matrix, and that means a matrix of 30 cross 30 values will be there. That is one box for one pixel. Okay, and we have certain values, right? Now actually in the in the computer, we not only take 30.30, we also take a certain variable of RGB, that is red, green, blue. Okay, so most of the colors that you are seeing on your computer is basically combination of any red, green and blue. Okay, so it actually is not an image of 2D image, it's actually a 3D image. With 3D image with 3 channels, this called as channels here. Okay, we have red channel, green channel, blue channel. So ideally, instead of having a 2D, this is not actually how it will be in the computer. It will be like a proper 3D image. Okay, so here the depth, here let's say it is width, this is height, and this part is basically a depth where we are putting RGB channels. Okay, so this is how it will be like. And what now you're going to do now, what as a convolutional operation, what you will do if you want to learn a certain operation on top of it, what you will do, that you will apply this kernel into this image. Okay, you will go part by part and try to calculate the certain values of the pixel. That means if I let me reshape here one more time, so let me have it here. So this is the image I have, and this is the output. I will get a usually 2D output. Okay, so what I will have a one kernel here. The kernel can also be a 3D filter, so kernel became filter right now. Okay, so kernel became filter because we are considering the RGB scale here. This RGB scale here, we are considering the values of that. So we will put so what we'll do, it's basically a matrices. Okay, and the kernel will be obviously smaller than the image. So we will consider certain values, let's say 9 cross values. So we'll consider that, we'll calculate the values like convolution operation, apply convolution, and based on that we get the one output as a one scalar value, and we will keep it here. And that's how and now we will slide this again to cover the all images to calculate the convolution. Now why this convolution operation is done? To get to convert the image into different kind of different kind of images. So ideally I should have put some images here, but it will be like maybe one layer might be like it will only detect the edges. Okay, detect edges, maybe the another filter, and you can put multiple filters here. So here if I have one filter, I can put multiple filters here like that. So this is maybe a filter to green one. Okay, this is F1, F2, Okay, now f1 will might detect the edges of the images, f2 might be just blur the images. Okay, f3 maybe if this is another filter, it will try to sharpen the images. Okay, when we are saying filter, is basically a 3D vector only. Okay, it's basically a 3D vector with certain values, nothing more than that. Okay, we're just naming it as a filter. Earlier we are calling it as a kernel. Okay, nothing much, it's just interchanging of the words. So it's basically a typically a sorry, not vector, I will say matrices, a 3D matrices or kind of like that. Okay, so what you will do, we are trying to perform multiple operation on the same image to try to learn that image. Okay, so that's we try to do here. uh, so there are certain terminologies. I will go here and then maybe I will try to start do one or two terminologies, and then maybe I will start doing the coding. Maybe there you will might understand it in a much better way. So there are certain terminologies are there. Okay, so input will have width. Okay, so input, there's something called as input width, input height, and input depth. Okay, that is for the images, w1, h1, and d1. Okay, this is for the input image that we are getting, and then if you want to get output according to your needs, uh, so you will have output width, that is assigned w0, height, and d0, that is for depth. Okay, this is there. And now the spatial extent of the this is something called spatial extent of a filter. Okay, spatial extent of the filter, that means when we are creating a kernel of 3 cross 3 into 3, that means 3 cross 3, and you have a filter of RGB here also, adding RGB channels, it will become 3 cross 3 cross 3. Okay, so that is, so we are just assigning with 1 because 3 cross 3 is cumbersome, so we just are adding with 3. So if any number you're getting, let's say 3 or 5, mostly in odd numbers, you will you say that its width, height, and depth will be same numbers. Okay, this spatial extent, the number of filters. Now in an image you can apply multiple filters, multiple convolution operations. So each filter will apply one convolution, different type of convolutional operation on that. Okay, so that is one number of filters are there. And there's something called as padding and stride. Okay, let's try to understand padding and stride first. uh, Let me create one, the big 2D array. Okay, now let's say you have this image of certain dimension, and you want to apply a kernel of 2 cross 2. Okay, so what you will do, it has some values. First you will go here. Okay, then uh, then if you want to go, you will maybe go here. Okay, then you can go here like that, right? So in this scenario everything is seem perfect, right? But what actually happens, that if I make another this kind of this, and it will perform certain operation, right? But actually the kernel size are actually in odd numbers, so let's say 3 cross 3 here. Okay, now what happens, so 3 cross 3 will be like this, right? 3 cross 3. So my in between image is my area of concern. Okay, is my area of concern. What is the middle of the 3 cross 3 kernel, that is my area of concern, and that thing I am actually trying to calculate by considering the neighbors. Okay, so if I want to calculate this value, that is corner 1, it is little impossible for me to calculate. The reason being, if I try to put 3 cross 3 here, I will only able to calculate this part I'm highlighting by square. I'm not able to calculate that, right? To overcome that part, because I can't put okay, let me create here. So if I want to apply 3 cross 3 here and I want to calculate the values of here, I need to put my this value like this. Like I need to construct some uh, extra columns, extra rows here to calculate this particular point of dotted point, right? Which is usually not possible. But if we add padding means what I will do, that since I knew that my corners and the boundary aspect, I need to calculate the images particularly at that point of time. I will create one extra row and extra column from the both top, bottom, left, right side, such that I can accommodate my kernel properly and such that I can compute it much better. So this, if I'm adding this, that is called padding equal to 1. That means I'm adding one row at top, one row at bottom, one row on left side, one row at right side, right? So this one and this one top, this thing if I'm doing, that is a padding of the rows and columns. Okay, so this is one thing. And if I want to use concept of stride means that, okay, I have used this part. Now if I want to calculate this point that directly, instead of sliding it one by one, I can directly jump from here and go went to the second point here, and I will try to calculate it. So I may skip this particular point. I'm putting it cross. I may skip this point stride. So it's like sliding window, right? If you're trying to slide, I will not consider these 2 points. I will directly jump to the dotted point here, right? So I will do 3 strides here. So that is the concept striding is here. Okay, so that means how often I can move my kernel in which direction, and how many jumps I could take to calculate the next value. Okay, and this is the reason of doing this padding and stride. I will just tell you in a few moments. The reason of this to do this is it reduce our calculation to a very large extent. Okay, to show this value, let me show you with a different kind of image that will might be help you in a much better way. So okay, so let's say I have a image of 4 cross 4, and that image is basically the value 2. Okay, so that means I have 16 inputs. I have 16 inputs like this. So what I am trying to do is I'm applying a kernel of 2 cross 2 here. Okay, and my the upper hidden layer will be something like this. Okay, and I'm applying stride of 2. That means if I am trying to calculate this point, I will skip these two x and I will try to calculate the corners. I'm trying to calculate the corners. So how I will do that, I will just take, okay, so let me take different color, make you understand. So what I did here, I did something different. So what I did, I am trying to calculate a neuron of, let's say, H1 and H2. And H1, I just need, I am skipping, I just taking few neurons, okay, that is maybe in my, because they are in my neighborhood, I am calculating certain values, right? And since because I am trying stride is equal to 2, I am skipping these two inputs, so I am just skipping here. Maybe it is of no use as of now for me. So that is totally is no use of me because I'm putting the stride equal to 2, I'm jumping. So for H2, if I want to consider, I might consider these two values as well, right, approx from the remaining, right? So because of this, the number I don't need to connect my H1 with all the 16 inputs. I just need, my concern is only with the 4 inputs at a time. Okay, and the same for H2 also, I'm considering with 4 input at a time. So this concept will bring us to a concept of sparse connectivity. That means when I'm trying to calculate or try to learn certain inputs, I'm not considering all the inputs like fully connected network. What I'm just trying to do, I'm just trying to take some specific inputs at a time, try to learn it, and then other neuron will try to learn another some aspect to it. Okay, that is one sparse connectivity. Another important function is that so whatever I'm trying to learn here, let's say it's W1, W2, W3, W4. So I have 4 weights of this kernels, right? The same 4 weights I can apply here as well, W3, W4 in the for H2 as well. That means I don't need to calculate for both the neurons or any other neuron. I don't need to calculate this weights again and again separately. If I able to calculate for the one kernel, I can apply for the other neurons as well. Okay, so that is a concept of weight sharing will come into picture. Okay. Uh, okay, maybe one more last concept and then I will try to wind up here and we will start the coding part and then I will just summarize it. So this is another concept called max pooling. Okay, so what happens is after given an input, that is the image in this case, okay, I apply certain filter. This is the input, I apply some filter. Okay, now what I will get certain 2D output. Okay, so let's say one I take black 1 4 2 1 5 8 3 4 something like that. Okay, some random values I'm putting here. So once I get that, what I'm doing is I'm using a concept max pool here. So what I will do to reduce further computation, based on the whatever filters I apply, I will take a small subset of max pool here, which will be same size of kernel. That means let's say 2 cross 2. If this is a 2 cross 2 filter is there, into the depth of whatever the depth of 3 RGB channel. Okay, so if I have this, I will take this part and I will take the maximum value from this 4 subset, that is 5 4 8 1. So let's say here, okay, so in 1458 what is the maximum value here? That is 8. So I will keep it like this. Okay, then I will again take another remaining subset of in the row, that is 2 1 3 4. What is the maximum value I am getting? I just keep it here 4, like that. So this is a concept of max pooling, that once I get some intermediate output, this intermediate output I am getting after applying the convolutional operation here. Next convolutional operation, I get some intermediate output and applying max pooling here to get the values in a much shorter form, such that I can apply much more operations on top of that. Okay. So right now, as of now, uh, we have seen few concepts. We have seen the concept in the terms of convolutional as an operation. Okay, we have seen something called as kernel. Okay, which actually turns into the filter. Each filter has its own role. It will convert, or I will show you visually that it will particularly convert an image into a different format. We will see that how it is happening in the code. Okay, then we have seen the concept of uh, okay, so we have seen the concept of here padding and stride, and we have seen the concept of max pooling. Okay, there's something called as RGB channel as well, because RGB means it gives a color to the particular image, right? So that is what we have seen as of now. If you're able to get a little bit overview of that, that is totally fine. Once we do the coding part, maybe I can explain much better way. So based on that, we will start our coding part from now. We will see that how to build a typical CNN using a simple using a PyTorch. Okay, that is what we are going to do. So let me stop sharing the screen. If you have question as of now, please type down in the chat section. Okay, so let me stop this sharing. Okay, so what we will going to do is Okay, yeah, I hope you can see my screen as of now. Okay, so what we'll do as of now is basically uh, look at that. We will use something called a CIFAR10. That's a very popular data set. We will use this data set for do some kind of image classification. Let me connect it here. By the time we will use something called as data loader from torch util. So last time we have introduced a PyTorch into the picture. So torch util is one of the torch utils is something which we are going to use right now to load the data into the our own CPU or the GPU. We will use a GPU. We will visualize the images directly, okay, and we will see single multiple convolution network. Then we will see the LayNet. LayNet is the first popular convolution network architecture. We will see that how to train that in a GPU, and we will do something called a simple visualization. Okay, so that is what we are going to do as of now. Okay, so let me import few stuffs before starting out of. So to import PyTorch, we will use import torch. uh, we will use matplotlib to visualize to help visualization our uh, the data as well as the loss functions and all that, and we are importing numpy for a simple manipulation of the tensors and the numpy array. Okay, now for data loading we are going to do later. To do that, there's a library called torch vision. We will use that, and we along with this we going to use also to use a torch version function where it will help us to convert image into a particular type of format, maybe the numpy array or as a tensor, because tensor is the uh, root of the uh, PyTorch, like root content or data structure of the PyTorch. Okay, everything deals in the terms of tensors here. Okay, so let me run the above one, the this thing. Okay, now what we are going to do, we use CIFAR10. So what is CIFAR10? Let me write the code first, and then we will see the what is CIFAR10 as a data set. Torch vision dot data set. So it will automatically so it will download the CIFAR10 dataset from Torch Vision library, and I'm storing it into the Google Colab notebook. Since I want to train the data, so I will keeping this thing as true. I need to download the data as well, so I'm keeping that part also true. And I need to apply some transformation on the data. So this transformation of what I want to do is I want to do in the range of two tensors. So I will apply two tensor function. Okay, so this is what I'm going to do. So let it run, and in the meantime I will show you. So it will downloading it is downloading the CIFAR10. Let me share the notebook as well. Okay, I will share the YouTube link in the break. Maybe 5-10 minutes we will take one break. At that time I will share the YouTube link as well. Okay, so CIFAR10 dataset. Let me copy this also for you people to understand. Okay, so CIFAR10 dataset is basically consist of 60,000 images. Okay, it consists of 60,000 images with 32 dot cross 32 color images. When you say color, that means it has three colors RGB. It will combine, it will create the colors. So 32 cross 32 cross 3. Okay, and it has 10 classes uh, with 6,000 image per class. So what are those 10 classes? That is airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck. Okay, so now what happens is given this data, uh, it also provides us that how many images they are giving for training and how many test images it is giving. So 50,000 images giving for training and 10,000 for test image. Now it is also, now for help us, it is also divided the dataset into 5 training batches, because image size are big, then the computation will be long. So that's why it divided dataset into 5 batches, which each batch consists of 1000 image. Okay. uh, so the test batch contain at least 1000 randomly selected image from each class. So what do I mean by that? If you go here in the file section, you find some data folder. In the data folder you'll get CIFAR10 batches. So it has 5 batches for training. Okay, and there's a one test batch. 5 batches consist of 10,000 images each, and test batch consists of 10,000 image. So this is what we have as a CIFAR dataset. You can spend some time on this also. It's pretty popular dataset on which you have to learn and study upon. Okay, apart from MNIST dataset. So let me also define certain classes here, that is plain. So I'm just writing that in the order. So bird, cat, deer, dog, frog, horse, ship, truck. So we have these 10 classes are there. Now once the classes are also defined, because we have manually have defined it here, we use something called as train loader. Now why I'm using train loader? To now we have the data set of 10, each batch we have data set of 10,000 images. So for purpose of our understanding here, we are going to play with very less number of data points, that is less number of images. To do that, so I will use toss.util.data.data loader. I will load the data. So how many data I want from train set? I want only, I am defining the number of batch size, that is 4, only a batch size of 4. I want only 4 images at a time. And shuffle I'm doing such that it can give us random images rather than giving only images of one type, one class. Okay, so it can give random images. So I'm using train loader to load any random 4 images from the data set. Okay, so this is what we are trying to do here in the image loader. So once we do this, let's run it here. Okay, now after that we load 4 images in train loader, we need to identify that which are those images are, which and what are the labels associated with it. To do that, we use something called as iter as a Python function, where it will go to a train loader. It will iterate with each and every image. Okay, and it will store the data into data iter as a variable, and from that we can identify what are the images and what are the label. To do that, we will use a function called next and data iter. So from train loader, the 4 images, we are keeping that in a iterator variable called data iter, and then from the iterator variable we are extracting each image and its own label. Okay, so to identify the what is the image size that we are taking right now, so we just write images dot shape, and we also do for individual images as well. Since we are dealing with tensors right now in PyTorch, everything will come in the terms of tensors here. So we will take the labels as well. So I'm taking a second image because image start with 0. So second image shape, and what is the label associated with that image. Okay, so if I run this, so what I'm getting, that is I have 4 images with 3 this is 3 RGB, that is RGB, this is channel for colors. I have a 32 cross 32 image, 32 cross 32 image, and 3 will give me the telling that it's a color image. Okay, with red, green, blue channels, and I have 4 images of such type. So image of one such image is basically 3 into 32 into 32. So that's what it tells about the second print statement. And the print label 1 tells us that it is 7th class. 7th class maybe in this case, maybe a frog in this case. Okay, so it is telling me that the sorry, starting 0, label 0, right? It might be horse in this case. To visualize that part also, let's do just do simple image plot here. Just a minute. Yeah, uh, images 1 and print type image. If I do this, I'm just telling you it's a tensor class, but I want to visualize it. So what I need to do, I need to do certain manipulation here. So what I will do, it says in tensor, I need to first to print it, I need to create in the numpy array. So np img dot numpy print np dot img dot shape. Just a minute. I think I'm getting one call. I'm just replying back. Yeah. So first I'm creating that using img.numpy. I'm creating the tensor. This is in this case a tensor image is present tensor into a numpy image. So once I will to do that, then I will transform it, because in matplotlib we have xyz, but here the z part here is present here as the first, that is 3. So we will just using a transpose part here directly. Uh, So, how we'll do that? So to transpose the image, we use np.transpose np-img 1 2 0. So what I am doing here is, so I have this variables. These are 3 different dimensions. So I am just putting that 32 as x earlier first, then y, then z, which is at the 0th place, as the 3rd place. Okay, that's the transformation I am trying to do here. And if I am trying to do print np image, so I'm just getting, I just converted this 3 cross 32 into 32 into 32 into 32 into 3. Now I can basically plot the image properly. So plt.figure fig size, I'm just keeping 1 cross 1 because it's usually a very small images we have got from them. And if I do im show, plt.im show, and pass that numpy array and plt.show, if I run this, so I get a certain image. So if you can look at this here, it is a it's a very blurred image, a small image, but we can see that it's basically a horse, right? So what we have done as of now to visualize the data, we have converted the tensor into numpy array, and we have done certain transformation such that we can print it according to our understanding. Okay, so I'll just create a simple function here such that we don't have to write the above thing again and again. So I'll just create one function, def imshow img. So I think I can do numpy here directly. I'll just copy it here. So whatever I have done here earlier on the top, I'll just using it here. So plt.imshow np.transpose np image 1 2 0. So this is whatever we have done earlier. I'm just defining into a few lines of code, and then I'm just printing it so that we can show whenever we want to show our image. Okay, now what else I need to do is to before going to the convolution layer, I just need to know that what kind of data I'm dealing with actually, right? To do that, I will what I can do is I will print all the 4 images that I have taken as a batch, on which we are going to apply certain on which we are going to make our model run. So to do that, we are using torch vision library again, dot utils function, in which our make grid function is there. So the because of make grid, what we can do is we can try to print the output directly, all the 4 images directly side by side. Okay, so let me write the, so I will just give little bit space here, dot join, in that join from class, I will just put the class with particular labels j of particular j for j in range 4. So I have 4 images, that's why I'm putting in the 4 like this. And if I run this, I think I did something wrong here. Transpose, okay. If I run this, so this is the 4 images that I am dealing with right now. So the first image is basically a dog, second image is horse, third is bird, and the fourth is horse. So on this 4 data set, we will see that how we can apply the convolutional network. Okay, so that's what we are going to do. It's almost 5 here, so maybe we can take a 5 minutes break, and after that we will, what we'll do, we will try to see we will try to see how to build a first convolution layer. That is the first thing we will do. Then we will create a proper network of that, where we automatically do the backpropagation kind of stuff. Okay, and then we will try to do a layenet. Okay, so let's maybe take a 5 minutes break at 5. So maybe we'll come at 5 and we will start again our coding part. The link has been shared on already in the this chat section as well. Okay, so I'll just stop sharing for 5 minutes so you people can take 5 minutes break and we'll come back. Okay. Thank you. Okay, welcome back. Let me share the screen again, and I will again share the Colab notebook thing. So we'll start. So we have seen, okay, let me share. Sorry, I haven't shared. Yeah, so far, so what happened is, so we have taken CIFAR dataset, CIFAR10 dataset. That means CIFAR10 means it has 10 classes. So these are the classes that we have seen, and we have directly downloaded online. Okay, and we have right now to deal with our basic understanding convolution network. What we are trying to do, we're just loading the batch of 4 images directly. Okay, and we have seen we have tried to visualize them. Okay, so it usually you will get in the tensor. So if you want to show the image, you can show it using you have to convert that into a numpy image, and then you can show it uh, using the IM show. Okay, so we have written certain codes with respect to that, and we have also whatever the 4 images that we're going to deal with, we are just trying to show the grid out of that. It is dog, horse, bird, and all that. Okay, so all that is good, well and good enough. So what we're going to do, we are right now at the stage now where we can write a simple convolutional network using a PyTorch. Okay, so to do that, uh, what we have to use, we have to import a certain library that is called torch.nn. That is, nn means neural network. Okay, so as class neural network. So then I will create a class called, maybe right now, because we are make different version of CNN, so let's say first CNN, and I'm going to pass nn.module uh, as a parameter here. It considers a module, and in every if you have seen or attended earlier or earlier sessions, so we always have to do a initialization function here. So we do def init, we are calling it as selfly, and we are calling the superclass of the nn module in this case, which basically a CNN network, this thing, where we can get the all the parameters. So we are calling that. So these are some basic steps that we have to do. If you're not able to understand that part, that is still fine. But here, from here, actual thing will come into picture. So right now what we are doing, we are trying to create a a convolutional layer. Okay. So to do that, we use nn dot conv 2D, because the output will be in 2D. So we have certain parameters here, that is, we have put 3 as a depth, 16 as the output of number of filters we want to apply, and 3, that is a kernel size. So let me write it down here, something as 3 is for con 2D that we are doing. Okay, so 3 as a parameter, when we are writing as a 3 as a first parameter, it is basically the number of channels. And since we from the data set we know it's a color image, and it explicitly say that it's a RGB channel, so we have 3 channels here, RGB, red, green and blue. So for that we are adding 3. 16 is the number of filters that, or number of kernels that you want to apply on the image. What are those filters, kernels, that is not our concern as of now, but just assume that there's certain kernels are there. Okay, and the last 3 parameter is something we call as kernel size, a uh, spatial content that we have talked earlier. So for that kernel, uh, so of size 3 cross 3, if you just write 3, it will understand that we are making a kernel of 3 cross 3. Okay, so this is the first convolution network that we are trying to do, and then this is the first definition, that is the initialization of the convolutional layer, and then we will apply a forward pass in this. So it's self.x, where x will be the input, and we are applying giving self.co and v1, that is this variable that we are having. We're just calling this function variable, and just applying passing uh, the input x into this, and we're just returning the x. So this is the basic code of just creating a convolutional network with certain filters, certain kernels, and just applying input to that, and let's see what will happen. To do that, first we have to instantiate this class. So we will do net as a variable which will initiate that first CNN as a class. So let's run that. So after running that, what we'll do, out equal to net dot images. So in images we have seen 4 images, like this 4 images are there for us. So that is what we are concerned. So in the net variable, like that is this, and applying image as an input. So this, in this case, so when I apply net images, it will go to the forward class. It will go provide x as a instead of x, it will be images here, and then apply the convolutional, it will go to the convolutional layer. Okay, that is this part that we have defined here. I am highlighting with the this nn.con2d. Okay, now once that is there, I just need to show that out.shape, what is the actual output will be like. So out.shape, if I do this, it is showing that we are getting certain values out of this. So what, let's understand what does this mean. So 4 is the number of images that we are having. Okay, so this is the number of images that we are having. Okay, then we have something on 16 here. 16 is happening because of number of filters, and 30 was 30. This is the image size we have reduced to. So what do I mean by that? Initially our image is basically 3 into 32 into 32. So this was our dimension. Okay, now after applying the convolutional layer, where we have 16 number of filters and 3 kernels, so what happens is, after applying each kernel we get a 2D output, right? So that so because of that we have 16 2D outputs, so that's why we get 16 as a base. Now when, and since we apply no padding here, so our topmost and bottommost, leftmost and rightmost column will not be considered of the image. That's why, so we will remove top 2 rows and 2 columns from that. That's why it will 32 minus 2 will be equal to 30. So that's why we are getting this as an output, right? So that's what we are getting here. So 16.30.30 will be the, if I apply one image on this convolutional network, I will get my input as 16 cross 30 cross 30. So that is what we are getting here. Okay, now if I want to know the number of parameters, basically in the each network, in the particular 2D network, this convolutional network, so I have to write net dot parameters. So it will automatically give me that, and just I need to do print param shape. If I do that, parameters are basically the number of weights, biases and all those stuff that we are talking in this case, but here we also deal with filters and all. So we are getting something like this. So what does it mean? So it has 16 as a filter, that we have some number of filters are like this, 3 as a number of channels that we are getting here, and the kernel 3 cross 3. So these are the 3 parameters on which the model will try to learn automatically. It is something you try to open up. So that is what we are trying to we are getting from this case. Okay, and the torch.size will tell us the number of number of filters that we are dealing with. Okay, so that is what it is about. Now if you want to show that how a particular image looks like I right now what we are just, we applied all the 4 images into this particular convolutional network, right? What we can do here, that I just want to show that one image. I will take just one image from the and see that what it learned from that image. If I just want to know that, how I can do is, I will do I want to know the first image, right? So I will call 0 cross 0, that is the first image, and I will just take all the inputs of the 30 cross 30. Okay, so this part, okay, so you can understand from here, I'm highlighting it right now. So I want to know the first image, that is 0th image. I want to know the 0th filter value. Instead of I have 16 values I can apply, but I try to understand only a 0th filter value, and I want to apply 30 cross 30. So if I just put column, I will get 30 cross 30, and to convert that into NumPy so that we can print it out, we need to use detach function and NumPy function. So once we do that, we'll print the image out1.shape. So that will comes out to 30 cross 30. Okay, so that will come out 30 cross 30, and if I just want to print it out, I'll just do print I am sure, and I will just do the same. I will just copy this line, and I will just show plt.show. Okay, some error is there. Let me see what is the error. Okay, I just need to remove this part. Okay, so let's see what is our first image was. Our first image is kind of a dog which is lying, or maybe a white dog which is lying on something. It is very blurred, we don't know, able to know that. Now with the first filter, if you can see, you can see that it is able to identify certain image of the dog which is certain kind of flying in a horizontal way, right? So if you can look carefully again at the image of the dog, it is lying in a diagonally way, and that is our first filter of convolutional network is able to identify that part somehow. Okay, so this is what able to handle. So that is the role of the kernels of filters, that maybe the first filter is try to identify the detect of the image. So if you just want to change the, if you want to know the which other filter what able to do, so let's do, instead of 0 I'm just keeping it 1. Let's see if I run that, it is able to identify the part of the, maybe it's trying to identify some other factors of that which we will not able to identify. But here we can all see that there's a dog leg here, and the face is like more light green that we can see here. Maybe let's see something else. Let's say 3. What is the fourth filter will do? Maybe it's blurring a little bit more, so we are not able to identify that. So let's say, so by changing these values you can identify different kind of what each filter will do on the particular image, right? This is what happening after applying the convolutional operation on. It's just a simple convolution operation that we have seen earlier. So it is like this. This is what the output will look like. Okay, so for each pixel, that is 32 cross 32 or 30 cross 30 pixel, each pixel has been calculated after applying a convolutional operation. Okay, so this is what you have to understand from here. Now apart from this, if I add padding here, because I want my image as 32 cross 32 only, I just don't want something else. So what I can do, I just add padding here. So I just need to write 1 cross 1. I'll just add it as it is, and try to run this all the same thing. So earlier our output, before running, earlier our output 30 cross 30 if we are not adding padding. So if I run this, now our image will be 30 cross 32 with 16 filters I'm running out, right? So let's run this and let's try to see how the output will be look like. So we'll get the 32 cross 32. Let's show this. Now it is maybe a much more better thing we can see here, that you can find that there's certain kind of dog, or first filter can identify certain, in certain aspect kind of dog lying there is able to identify in this case, right? So that is the beauty of the padding here, which able to help us to give us much better outlook than the one without padding. Okay, now there's another variable called stride, that is we are skipping certain pixels to reduce our computation. So if I do 2 cross 2, so it will decrease my 2 cross 2, that means I will remove two rows from top, bottom, left and right. So that is 32 minus 4, sorry, okay, if I do 2 cross 2, I'm doing 2 times, so my final image will be into 16 cross 16. Okay, so if I just run this because of stride, let's see how the output will look like. Now it is very hard to identify that whether it's a dog or not, right? Why? Because of stride and all, we are not looking at each and every pixel, we are just looking at few of the pixels. Okay, we are skipping few of the pixels because of this stride 2 cross 2. So that is what we are trying to do here, and this is what the output we are getting, right? But this is very much needed when the computation is very high, when we have to see a lot of images and all that. At that point of time, it will take it will do its own this thing, what you say, it will automatically will try to calculate the computation as fast as possible. Okay, so this is all about the first neural network. first convolutional network where we haven't given any input layer, any output layer. We are just providing one convolutional layer, and we are just passing certain values here. Based on that, we are trying to understand that how it is trying to learn the image. Okay, after applying a convolutional operation on top of image. Okay, now let's create a proper deep neural network out of that, so that we can get a better understanding here. So let me copy the whole code and just put it here. Okay, so I just remove this torch because module. Now I will call it as first CNN, maybe version 2 kind of thing. Same NL module will be there, and the convolutional layer will, I will calling the super constructor out of that, and I am creating a convolutional layer here. So it will be without, I will just remove padding and stride for now, and I will instead of 16 filters, I will have only 8 filters, kernel of 3 cross 3, and conventional layer of 3 with RGB channel of 3. Once I have done that, okay, so I need to do one more thing. So what I have to do is I have to combine them, these layers, right? So to do that, I need to use something called as nn.sequential. So my model, I will name it as my model, and I will add nn.sequential. Okay, and let's have it here. So what NNL convolutional will do is basically it will, whatever the layers I am creating right now, it will stack it together properly automatically. We just need to define the layers, what are the content in the layer, that's it. Everything else will be taken care by the sequential function. Now this is the first layer I have defined. The second layer I will define it as con2d. Okay, now here since I will be taking input, now I have taken the input from the image directly. Now after this, the second layer will take input from the first layer, first convolutional network. So for that, my input will be directly taken from 8 because 8 filters are there, and I will convert that into 16 filters, and I have a kernel of 3 cross 3. Okay, so that is what I'm trying to do. So if you want to understand what we have written in the terms of uh, the length of the particular thing. So we have n is like number of images we are passing. We have 3 channels and 32.32 cross of images with 3 channels, right? After applying this convolutional network, what we do, we will get n images as it is with 8 filters with 30 cross 30 size of image. Okay, so we are just applying convolutional operation on top of it with 8 filters, 8 different filters, and getting a 30 cross 30 image size, right? After applying this, we will take the same we will take the same this thing as output of first output layer, as an input of second input layer, second convolutional layer. So we will take it as an input, and then what we'll do, we will get n images as it is. Since we are applying 16 filters here, so we are getting 16 filters as output, and our image will further reduce from 30 to 28 because our kernel of size is 3 cross 3. So our one row from top, bottom, left and right will be reduced. So this is our first new deep convolutional network, and here forward will be same. Instead of con, I will just call the model self.model. I will pass the image as it is and just return. Okay, so if I do this part, I'll just run this, and okay, I did certain wrong thing here. I need to provide comma here. Okay, now if I run this, okay, now net will be, I will just initialize this value. So first CNN version 2, and out is equal to net images. So I'm initializing that this particular class that we have defined with 2 convolutional network, 2 convolutional layers with different parameters, and here I'm calling if I'm calling net images, I'm passing the images as an input to the net. I'm initializing the net from the class is an object of class of first CNN version 2. So when I'm applying net images, it will go into the forward function, and it is calling the model that we have defined here. It will apply convolutional net layers operation on top of these images, and it will pass out the output into the object called out, right, which is basically a tensor. So if I run this part, okay, something is wrong here. First CNN version 2. Okay, so I think I have done something. Okay, I need to, here also I need to do v2. I made mistake in the copying pasting part, so I just need to add the class name as it is instead of adding some other class name. So I did that correctly here. Now if I'll run this, so I'm getting a tensor of 4 images with 16 filters of 28 cross 28. So this is what we have found here as well. So this is exactly what we have found in here, is same what we're getting here. Okay, so everything is good enough as of now. And if I try to show that how the image will look like after applying this convolutional network, is plt.im.show out first image, applying the first filter on that, and just show the all the input as it is, all the image input as it is, detach dot numpy. So if I do this, I plot this, so I'm getting, after applying 2 convolution layer, I'm getting this for after applying the first filter, I'm getting out in my image output like this, which is I can still figure out that this light green part is a kind of face of a particular dog, and the little dark green part in the left corner is something kind of like is able to give a certain value, but not that exactly the same. But that is still fine, since we are trying to see the how to build a convolutional neural network using PyTorch. It is still giving a very decent output as of now. Okay, now what we'll do, we will again take this code and create a uh, proper convolutional network where we have a pooling operation as well, because without pooling operation nothing will work as of now. So let me run that part as well. uh, so I will name it as version 3. Initialization also I will keep it a version 3. Okay, the self-taught model sequence I will keep, after applying convolutional network I need to apply okay, I will change certain values here. Maybe I will increase the kernel size, and I will take only 6 filters as of now. So if I do this, my input will be 32 cross 32, that is the input, and I will get that, and 6 because we have 6 filters, and since we are applying not padding and we are applying 5 kernel, so our image size will decrease from 32 to 28 cross 28, because we can't we have to remove 2 rows from above, below, right and left of the matrices. Now the same thing, after applying the convolution layer we have to apply the pooling to reduce our computation. To do that, we are applying, instead of max pooling, that is we have to, if we take one kernel window of that, we have to take the maximum of that window. So instead of that we will do average pooling, that instead of taking the full uh, instead of taking the maximum value from that window, we will take average of that window. So to do that we will use average pool 2D. We will take 2 as an input and stride as 2. That is, we will take 2 cross 2. We will take 2 cross 2 here, and as a window. In that we will take average of those 4 values, and after taking the value, we are applying stride here. Stride means we are skipping 2 values again from that whatever the image output we are getting. Okay, so that is there. So here also the value, so the output will be look like from n6 cross 28 cross 28 from here. After applying max average pooling, or the image or will be converted to n cross 6 filters will be remain as same, but the image size will reduce, that is it will come down to half of the size, that is 14, because of stride 2. Okay, because we are looking at only half of the images, half of the values from the image. Then again we'll apply convolutional neural network here, so because since we have 6 filter, we will do that as an input, 16 filters as it, and we are taking kernel of 5. So if we do this, and here the okay, so we will do that part, and then our input will be like n cross 6 cross 14 cross 14, and after applying the convolutional network, the image will look like n cross 16, because we have 16 filters and we have to remove 4 rows and 4 columns, so we will remove that part as well. So that's how we will get this value, and again we apply the pooling function. After applying convolution, we have to apply pooling function as well. So we are applying average pool 2D to stride equal to 2. Okay, so after this, if we apply this, so we will take this as an input, whatever the earlier output was there, so we will take this as an input, and after applying the convolutional network, we have n cross 16 filters and 5 cross 5. So this is the basic convolutional network model that we are trying to create here. Okay, and then again same forward function will be same as it is, and this will be as it is. We will initializing the version 3 first, so we will taking that this new convolutional network model pass the image as an input, and the output will be like first CNV3. What is the oh, I haven't run this part. Okay, something is wrong here. Okay, I haven't applied the comma. Okay, okay, so the final output will be like 4 cross 16 cross 5 cross 5. This is something was similar to what we have seen, and instead of n we have 4 and 16 cross 5 cross 5. Okay, so maybe take some time after the class, after looking at the code, please look at that so that you can get some understanding. Now after applying so much of stuff, let's see that how the output will look like on the first image, which is basically a dog lying on here. So let's apply that part. So here we can see that we are not able to understand what is actually happening here, because we applied too much of convolution and too much of average pooling here, but that is still good enough as of now, because we have reduced our computation. That's the first part. Also, what is happening is as we do, we haven't started the training part. We're just defining a convolutional network, and we're just passing the image. That is we are just doing the feed forwarding. We are not doing the back propagation as of now, right? So for that, this part is still okay. If you are not able to understand, we can't interpret that part, that is still okay. But when we start training it, we will able to the model will try, because of this R layer, it will able to understand that how it can train the image based on the 10 classes. Okay, so this is what we have created as of now, the first proper convolutional network here. Now what we will see, if we have any question, because before that, let's see after, because we will what we'll do right now, we will right now code out the laynet. Laynet is the first major convolutional neural network which we use for image classification. So let me see if you have any question. You can, so please anyone, if you can see that, you can give the code link here directly, because I have already shared that with you. So I have shared the code again, Umesh, you can check that. Okay, so what the laynet look like? So let me open the laynet architecture first. So let me write laynet architecture, images. Okay, so I think this will be much better, but I guess yeah. Okay, so this is basically a laynet architecture which is we use for full for image classification purpose. So I'll just give you some example what it does it mean like. So given an input of 32 cross 32, like same as our CIFAR dataset, okay, what it will do, we'll apply convolution on top of that. Okay, so we have some convolution layer, then followed by a pooling layer, followed by convolution layer, followed by pooling layer, and then we have a fully connected layer at the end. Okay, So if you can see my mouse here, we have, and based on that it has certain so they have already identified that how many filters do we need for convolution layer 1, how many how what kind of pooling we have to do in the pooling layer 1, what are the filters do we not in the convolution layer 2, how much pooling we have to do. So based on that it is automatically derived. They have try and test a multiple combination. This considered to be one of the best combination that they have found during their, it's a 20-year old convolutional network, but we are just for basic understanding we try to do this. Okay, so what we are basically, what the purpose of this network is, if I'm giving a here, let's suppose, after applying all the different kind of transformation, different kind of operation on top of this image, we try to learn the image that this image has a, right, and the output we'll try to give as the output of 10 classes. So instead of, let's say a, let's suppose it's a number, so what we'll try to do, instead of, we will try to understand that whether from 0 to 9 which number it is the image contains. So it will apply all this information, all this convolutional network followed by the this fully connected network, which is shown as a step. It will apply that and it will try to classify that whether the image contain any one of the images or not, that is 0 to 1 class or not, it belongs to any one of the class or not. So this is what the lanet means. Okay, uh, so we will just try to code this part. So let me write it down. So lanet.nn.module. Okay, so first we will define the initialization of our model. So how we can do that? Def underscore underscore initialization, we're passing the self as an object. We are calling the super class object, that is lane, where we are passing our class variable lane, class name lanet and the object, and we're initializing in the above as well. Okay, after that it has two parts here. The lanet architecture has two parts. So first part is sorry, here the first part is this 4 stacking layers that you can see, right? There's these 2 convolutional networks and 2 average pooling networks. So this is what we have. This considers a convolutional network, and the last 3 steps that you can see here, if you can see my arrows, last 3 steps is considered a fully connected network. So we're going to merge these two things into one. So how we can do that, let's see. So to write that, we will use nn.sequential. So self dot cnn model, first we will create a cnn model first. So we'll do nn.sequential and we just write it down here. And so first is our convolutional network, convolutional layer. So once we get this, so it has 6 filters and 5 cross 5 learner. Then after getting the output of from the convolutional layer, we are applying some non-linearity, that is we are applying the activation function called tanh here, says to bring the non-linearity in the learning. Then after that we are doing average pooling again. So this is something has already been proposed in 20 years back, so this is not something I am making up right now. For image classification, this is one of the good techniques for the starting purpose. Much better techniques have been come as of now. So we will see that maybe in the next session, next Tuesday, where we are going to see a proper CNN architecture. Okay, so we have applied convolutional network, then we applied tanh, then applying the pooling operation. Again, we are applying the convolutional network here and applying the non-linearity activation function. After applying activation function, again we are applying the average pool to there is pooling function. So let's try it equal to 2. Okay, now once we able to do this, this is first part is done. Second part of the model is the fully connected model. So we using a fully connected as FC model. We will again combine the layers using nn.sequential. So nn.sequential, here we have nn.linear, and they have identified 400. I will come back to how it comes to 400. Cross 120 neurons are there in the first layer. Then applying the convolution activation function. Then the second layer has nn.linear, second layer has 84 neurons, so we'll put 84 neurons. Then nn dot tan has an activation function, and nn dot linear 8 from 84 will come down to 10. So we are not applying any softmax function as of now, but we will use it later. But for now, since we are trying to replicate the model which is given in this image, we're just trying to correct it. So this image has two parts. One is convolutional part and the second is fully connected part. So we have defined it already. So the first highlighted part is the convolutional neural network, and the second part is fully connected neural network. So whatever the output we get till from calculating this, we will give this as input to the fully connected part. Okay, so forward x will do that. Okay, now we will just print the shape, x dot shape, to see that what is our input as look like, and then apply the convolutional model on top of this image. So we'll part the input, and then we will see what the input will look like. After that, it's a small x dot shape again, and after this, since to provide to the input from convolutional neural network to the fully connected, we have to convert the image into a proper one vector. So to do that, we will use x dot view. So in that, x dot size 0 and -1 for flattening the image into one single row, and then we'll print the x dot shape, and then we'll call self.fc model, fully connected model, and we'll pass the input again, and then we'll print the shape, x dot shape, and we'll do return x. Okay, so this is what we have written here. So what we'll do, we'll give an image, we will we'll pass it to a CNN model. We will see how it will work, and then after getting the output as output from CNN model, we have to flatten it out to such that it can get into the fully connected network. To do that, we will use x dot view function. It will factor out to one vector, and then after flattening out, we will pass it down to a fully connected network. Okay, and so here x dot shape is basically to tell us that what is the input, how we are converting the image 32 cross 32 image into various shapes to make it accommodate to learn the model. Okay, so I haven't defined here the values of what will look like. I will come back to that. First, let me complete the model first. So net is equal to laynet and out equal to net images. So I'm defining the laynet model. I'm passing the images as input, and I will discuss this part as well. And just let me print out few of the stuff, and just put max values, predict class. I'm just printing out what the data that we got from out, whether it is able to identify the classes of that particular image properly, 4 images properly or not. Okay, so we just predict class. Okay, fine. Let's see now what we have done here to get a better understanding. So what we have done here, we have created a CNN model, okay, with 2 convolutional network and 2 pooling networks. Okay, so our convolutional neural network will get an input of n, that is the number of images. 3 is the color channel, that is RGB 3, and 32 cross 32 image. Okay, after applying the convolutional network, it will convert into the number of images. It has 6 filters, so apply 6, and since we are applying a kernel of 5 cross 5, so we'll remove 4 columns from top, bottom, left and right. So that will come down and cross 6 cross 6 cross 28 cross 28. Then after that, we are applying the tan function to bring the activation function to bring the non-linearity. After that, we'll give this output of convolutional neural network as an input, that is n cross 6 cross 28 cross 28 as an input and applying the average pooling. Now once we apply the average pooling, the number of filters will be same, that is 6 here, the channel will be same, and because we are applying stride 2, that is, it is reducing the image size from 28 cross 28 to 14 cross 14. Okay, now after this, again we are applying the again we are applying the convolutional neural network here. So we are giving the input of n cross 6 into 14 cross 14. We are applying this and applying convolutional network with where we are applying the 16 filters here. So we are getting n cross 16, and since we are applying kernel 5 cross 5, so it will reduce from 14 to 10 cross 10 image. Okay, we are applying again the activation function, and when we are applying this 16 cross 10 as a input from convolutional neural network and applying the average pooling, so it will come down to 16 cross 5 cross 5. The image size is getting reduced and reduced. Okay, so this is what we have seen here. So this is the input. Now you can see here the torch size, it is the input that we are given 4 images with 32 cross 32 size with 3 channels. Now after applying the convolutional neural network, we are come down with 4 images with 16 channels and 5 cross 5 image. So this is what we get as a output that we have found it here. Now to apply to convert, now this is basically a 3D notation, that is 16 cross 5 cross 5. So to make it to a single row, single vectors, because we are now doing the fully connected part, so we have to multiply it. So how we do that? We have converted the input using .x dot view, right? So what we did, this 16 cross 5 into cross is equal to 400 values. So 400 values we have passed it down, converting here. So given input as 400 and passing to layer 1, which consists of 120 neurons. So that means n images with 400 values, each image has 400 values as an input, and we are converting that to n images with 120 values, that is the 120 neurons we are having. Then we are applying the activation function. Then after the first layer, we are applying the taking as an input of first layer and applying going to the second layer, where we are applying 84 neurons. So it will become n number of images with n 84 neurons, and after that n images with 84 neurons as input, and then at the final layer for each images we are identifying which out of 10 classes, which of these classes is belong to us. Okay, so that is what we have done. So that is what we are getting here. So torch size now it became for 4 images. For each image we have 400 values. So this is what we have taken as an input, and afterwards as the output we are getting for all images we have getting 10 values. So this is what we are getting here. So this is what we can see here. Here, that is, we have 40 values. Each these highlighted are 10 values for one image. Okay. Similarly, this value 10 values for 2 images. That is, these 10 values are, there is a probability of an image belong to a particular class. Okay, and which class it belongs to, the highest value. So what we have done, we have using tor.max for each of these images, we identify the maximum value and we are identifying the class. So in this case, it is giving us 5th class value. That is, in this case, what is 5th class would be, 5th class means 6th class, 1 2 3 4 5 6. So it is giving us dog. So based on applying our first neural laynet without training, we haven't trained as of now, we haven't applied back propagation. So it is defining all these 4 images into dog class. Okay, which might be equivalent or nearer to it, because if you can see, apart from the bird, the horse is quite nearer to the dog class. So we can assume that if you do certain more training on that, if we apply back propagation into the CNN network, laynet network, we can be able to understand we can make the machine CNN model to understand that what these images are. Okay, so let's train the laynet. So this is the last part of here. So we just train the laynet now and see that how it will going to look like. So what we'll do, laynet is here, and so we reduce certain aspect of from here. So let me copy this paste copy the whole this thing. Let me copy this and okay. So what I will do here, I will make some few changes here. So lanet as this class as it is, 3 cross 5 tan h, everything will be same here. FC model will be same, only the forward will change here. I'll just remove the print values from here. So nothing much I have changed. I just taken the lanet model that we have defined earlier and just pasted in a different class. We have defined this. Now what we will do, we will define the actual now we will try to train the whole data set of CIFAR10 into using the lanet architecture. So what we do, instead of taking 4 images at a time, we will take 128 images, and to do that we will create train and test set. So how to do that? We use torch vision function through which we have downloaded the data set. So torch vision.dataset, we define CIFAR10, okay, and we will write data root where the actual our value will be, where actual data consists of data set, that is root.data, that is in this case the folder here. So here the data folder is there, in this I have the data. So it is asking the torch vision.dataset to look into this folder, okay. After applying the data, I am telling that the train is equal to 2, that is yes, you have to train train on this data, and I have downloaded that, so that is why it is also called as true. And I'm transforming this data into tensors, because PyTorch deals with the tensor to tensor, okay. So this is the first thing I have done. Now first thing, now we have to, after putting that into this, we are creating another variable called train loader. We are going to load this train set data. So to do that, we will util.data loader, and in this we are passing the train set. We are passing the how much batch size, that is number of batch size that we want to deal with at a time, because each in this we have, if you can see the data batch 1 2 3 4 5, it has 10,000 images. So we can't take 10,000 images all at a time, our memory is not that high. So we are taking only batch size of 120, that is 128 images at a time. We will take it and try to learn, and we will shuffle it such that our model can train it much better, okay. So this is for a train set. Now we will do for test set as well. So I'm just copying the earlier one and I just change it to train to test set, and I will keep train equal to false because our train, we don't have to train now. Download will be true, transform it to tensor. Now the same to test loader will be here, instead of train set we will have a test set. Batch size will be same of 128 and shuffle equal to 2. So let's run this part. So this will be done. So this is already downloaded and verified, okay. All this part is done. Now we will define a evaluation here called data loader. So data loader we apply, and then so this is for this function we are writing just to check that when we are trying to train the model for each epoch, what is the value we should get, right? For each epoch, what is my test accuracy and the train accuracy. So to do that, for data in data loader, inputs labels equal to data, outputs is equal to net input. So what I am doing, from the original data, from the data loader that we have seen here, I am extracting the images and its label. Then I am only giving the input as an image as an input, and I am storing the predicted output into outputs, okay. Now once I am able to do that, I am doing pred and toss.max. So I am right now, I will calculate that from the outputs dot data what is the maximum value I can got, and which image assigned to which class. Okay, so I will do that, and total dot label dot size. So I'm basically now storing all the value into the one particular variable called total, that is total prediction and the correct prediction. So correct prediction will be pred equal to labels dot sum dot item. Okay, item, and then I'll just return the accuracy, basically it is 100 into correct divided by total. So total prediction divided by correct prediction, this is my accuracy. So I'm just directly we can write it in a different way later, but we just to get your understanding that how we get accuracy of that, and we just hard coded this value. So we are just passing the net equal to laynet. Okay, now laynet is not defined. How come? Okay, n is small. Okay, so this is what we have done. This laynet we have initialized into net value. We already defined the evaluation as well. So let's see now what we can do. So another thing we have to add here is optimizer. That is earlier we used to do sigma gradient descent as optimizer. Now we have much better optimizer, as you have seen in the course. So first we will define the loss function. Function, this is a classification problem. So we are doing cross entropy loss, and opt is equal to optim dot adam. So I am taking adam optimizer net dot parameter. So I'm just calling this part. So I will use adam optimizer. Now let's write the main fit function. This is a main code here. So I'm just putting time here just to see how much time will it take. And what I will do, I will just keep the track of all the loss accuracy per epoch. That is for that loss epoch per accuracy. That is one variable I'm defining, and max epochs that I want is equal to 116 epochs I want. Now what I will do, for epoch in range max epoch for I in data enumerate. So now I'm passing the training data one by one using train loader for starting from 0. Okay, now input labels coming from the data as it is. Now I will apply optimizer dot 0 grad, that is all the gradients that I'm going to calculate right now I'm just keeping as 0 because for each epoch I need to keep it 0. Then I'm applying the laynet function by passing the inputs, and then I will applying the loss function here. So I'll just select loss function outputs into labels. So labels are our actual output, and outputs are the predicted output. So that we have done, and then we are applying the loss dot backward to apply the backward propagation. So we are applying the loss dot backward propagation, and after doing that we are doing step. So after doing this applying step, that means we will calculate whatever the, after applying the optimizer of Adam, we'll upgrade we'll calculate the gradient and update the weights and the bias of the network. Okay, so once we apply that, then we do loss accuracy that append loss dot item. So in the loss dot array list we are just putting the accuracy of that, and we will, for each epoch we are calculating the loss value, so we just append that value as well. Okay, awesome. Now we can just print the same thing, epoch equal to print d that is, I'm just, for each epoch what is the test accuracy and what is the train accuracy, we just want to print this out. Okay, So what right now what we are doing in it is we are doing it uh, in a CPU. I'll just change it to GPU because CPU will take time. It will take at least, when I run this code, it took me 8 minutes, so we don't have that much time. I guess we almost end of the session. I'll just code it and just change it to the GPU. I will show you how to do that, how to use Google Colab for GPU. Just a minute, just let me complete this. So I'm calling evaluation function and trained order. Okay, awesome. Now I can then plot um, the values loss dot epoch dot arr. Maybe after the session is over, you can run this part of code. What I will do is I will not run this code of the CPU. I will just do it for GPU. That will be much better for me. So let me quickly write the GPU code here, because I just to write few lines of code. So I just need to write device equal to torch dot device. Okay, one more thing I need to do here. Um, okay, so if you want to use, before writing the code, if you want to use GPU in the Google Colab, what you have to do, you have to go to edit, you have to go to notebook setting. Here it's CPU is there, you have to write select T4 GPU or T4 GPU, do that, save it. Now it will again restart. Um, it will connect now. Okay, so yeah, now I have access for GPU. Now what I will do, before till this last code, I will just run all them, such that yeah, because if I run this part, this highlighted part of code, it will take 8 or 10 minutes of time. I will just run this whole code into GPU. So to do that, I need to create a GPU setting. So I just need to find CUDA 0, that is the first GPU, if I have a GPU or not. Since I have taken already GPU, GPU will be available. So I'm just checking right now whether it's available or not. So whether it's available, else CPU. So if I don't have GPU, I can do the CPU part. Now device, print device. So I have a, since it's printing CUDA 0, that means I have a GPU. Now only thing what I need to change here is the evaluation part. So what I need to do, using GPU code, I need to pass it down to device. That means the same thing, inputs dot label, inputs and label in data. I just need transfer it to inputs dot to device. That is device in this case is GPU. Okay, so labels dot to. Just give me 5 minutes. I'm almost done with the GPU code, because it will run fast and we can discuss the output once before closing the session. So once we do this, input labels we are giving as it is, label to device. Yeah, I think all this thing is done. This also we need to run it, and evaluation part is done, and we have to pass this whole LANet network to the GPU. So to do that, you just need to use toDevice function. To device, this device is basically the GPU here, and loss function will be cost, entropy and atom. Okay, so let me do this part also. Now only thing I need to do is I just copy this part here. Here also I need to change few things, because I need to put inputs and labels into the device, into the GPU device. So I will just copy this line and I will add it here. So from CPU I'm passing to GPU, and yeah, I think that will be more than enough for now. If I run this code, because in GPU if I run this, it will run very fast comparatively. So what we have done, we have taken the LANet architecture, this LANet architecture. Now we are just putting all the LANet architecture into the GPU, and instead of giving 4 images, we are passing all the images for training, that is 50,000 images for training, and we are doing that training for 16 epochs. main aim is to okay, something wrong has happened. Not all arguments in the string format. Okay, where it is exactly is coming. Okay, right now what I can do is I can just comment this few steps out if it is happening a lot. Okay. Okay, it will happen it will take some time. So what will happen, it will this 50,000 images for training and plus 10,000 images for testing from the CIFAR dataset, this dataset we will training on a layenet architecture, and it is running on the GPU as of now. How GPU? Because we use this concept of torch.device. We are identifying the GPU device, printing it, and then we're putting our inputs and input data to device using this command, and applying the zero grad optimizer loss function, and applying the back propagation here. Okay, so let's wait for certain time because it will take a minute or maybe a minute and a half to complete this thing, because since it is GPU, it is run very much faster compared to the CPU. If I run this code, I haven't run this code, you can this part of the code I am highlighting right now because it will run on CPU. So let's wait for that time. Okay, so by the time it runs, let me revise what we have done. So in the first half of the session, we have taken discussed the basic convolutional network. The convolutional network, neural network is basically applying a convolution operation, like just like how we have applied wx plus b. Instead of that, we are doing something called as convolution operation on top of images. CNN is usually used for images, that's why we are using that. So once we are able to do that, uh, uh, so in that we have seen the concept of filters, kernels, padding, stride and all. Now what we have done earlier, in the top we have selected the dataset. We have taken the CIFAR10 dataset, uh, which is consist of 60,000 images. Like this dataset I am talking about, it has 60,000 images of 32 cross 32 color images, right? Then we did certain uh, transformation on that, and this is how the image, a particular image will look like, right? So these four images we actually look upon, and then we started defining the convolution layer one by one. So first we created only one convolution layer, then we have created a convolutional network properly, where we have a network of two convolution layers, then a proper network where we have, apart from convolution network layer, we have a average pooling as well. Then followed by we have seen something called layenet, which is one of the first convolutional network architecture, that this is something we have defined, and on this structure we have applied the CIFAR10 dataset. We have trained on that on the GPU as of now. Now it has run. So if I just need to print the output, so let me just print the output, how much it is giving me accuracy. Let's check that. So it takes 2 minutes of time, but if you run on CPU, it will take at least 8 to 10 minutes of time. Okay, so GPU is much faster in this case. So I'm just, let me write the output of how it will look like. So train, test accuracy, and just want train and test accuracy after training on 50,000 data set. Accuracy percentage 0.2f, and evolution test loader, evaluation train loader. Okay, if I run this part, so if I apply layenet train, try to do layenet on that apply on the CIFAR10 dataset, I am getting a training accuracy which is not so good, but still better than a test accuracy. So if you see the train accuracy is much better than test accuracy, it means that it might be overfitting. That means it is trying to learn more and more of the train data, but it's not able to generalize for the test accuracy. So that is one important part. Okay, I think it's all, I already passed 10 minutes more. So let me stop here. So what we will do maybe in the next session, that we will look at the proper CNN architecture one more time and we will code it properly. Okay. So if you have any question, please let me know. Otherwise, the session is end from my side. Please try out this code, change some parameters and all that so that you can get some better understanding of that. Okay. And if you have any doubt with this code, please tell me in the next session. I will let you know. Tuesday is my next session. Okay, thank you. In that case, I am ending the call for everyone. Let me stop the recording first. Okay, yeah, take this time. I'm just stopping the recording by time.